Okay, this is a 3.2 number 33, and we just want to find out where this function is differentiable. And we usually won't have any problems as far as the sign of a function because that's a nice smooth curve, so it's usually differentiable. What's differentiable for all values. But what we have here is we have a interesting function because we're talking about the sign of the absolute value of x minus 1. So whenever we have the absolute value, we have to treat this as a piecewise function. So if we look at p of x, this is going to equal the sign of x minus 1 when x is greater than or equal to 0, because that's what the absolute value of x is. But when x is negative, the absolute value of x is negative x. So this is the function p of x when x is less than 0. Now remember our trig from our trigonometry. We know the sine of negative theta is equal to negative the sine of theta. Now I can kind of review this for you. Remember, if we look at our unit circle and we look at our triangles, we know the sine of theta is equal to the opposite side, a over h, over the hypotenuse. And negative theta would be down here in the fourth quadrant, and that would be negative a over h, because we're just going down because we're in the fourth quadrant. Okay, so we could say that the sine of theta equals, or sorry, the sine of negative theta equals negative a over h, which is negative a over h, but the sine of theta is just a over h. So instead of writing the a over h, I can write sine of theta, so I got negative sine of theta. So you can kind of derive it like that. So again, the sine of negative theta is negative the sine of theta. All right, so I can rewrite this function as sine of x minus 1 for x greater than or equal to 0, and negative sine of x minus 1 for x less than 0. Now, this is a continuous function, and that's a continuous function. So I just really have to check the junction point. What's happening when x equals 0? Well, if I take the limit of this function as x approaches 0 from the left, I'm going to have negative 0 minus 1, which is negative 1. As x approaches 0 from the right, I'll have sine of 0 is 0, minus 1 is minus 1. So the left limit equals the right limit, so the limit as p of x, that's this whole thing, the limit of p of x as x approaches 0 is negative 1, but that's also the value of p of x, or p of 0. Because if I put 0 in my function, this is the one I use, and 0, sine of 0 is 0, minus 1 is negative 1. So the limit of p of x as x approaches 0 is negative 1, and the value of p of x at x equals 0, which is p of 0, is also negative 1. So it's continuous at that junction point. So we can't cross that out. So we can't just say it's discontinuous. So it may be differentiable there, even though it's continuous. All right? I'm sorry, it may not, and it may not be differentiable there. I think I'm going to say. It may not be differentiable there, even though it's continuous. If it wasn't continuous, I'd be done. It wouldn't be differentiable there. But since it is continuous, then it still might be differentiable, it might not. So I've got to check my left and right hand limits. Okay, so let's do this. Okay. And the one thing we do know, that if it's not differentiable, it's not going to be because it's not continuous. It's continuous. So let's check the differentiability based upon the left limit and the right limit. So if I take the left-hand limit, that's going to be, again, f of a plus h minus f of a over h. And that's going to be 0 plus h, f of 0 over h, f of 0 plus h. Now remember, this is going to be negative, so this will be to the left of 0, so I'm going to use this function here, the negative one, which is actually this one. And that's going to be 0 plus h, so that's going to be negative sine of 0 plus h minus 1. And then f of 0, when it's 0, it's just the positive. So it's sine of x minus 1, so I put that in over here. Okay, so this was when x is less than 0, and this when x is equal to 0. And then 0 plus h is just h, so I've got negative sine of h, and minus 1, and then sine of 0 is 0, and negative 1 times a negative 1 is a positive 1. Okay, so we've got this. Now these ones cancel, so now I've got negative sine of h over h, but I can take the negative out front. It's like a constant multiplier rule for limits. And then I have the limit as h approaches 0 from the negative direction to the sine of h over h, and we know that that limit is 1 with the negative in front of it, so that limit's negative 1. Okay, now I check the right-hand derivative. The right-hand derivative, let's take a look at that. Same thing, except when I add, as h approaches 0 from the positive direction, this is going to be a very small positive number added to 0, which will make it to the right of 0. So I'm going to be using this function for both, because it's to the right of 0. So that's going to be the sine of 0 plus h minus 1 minus the sine of 0 minus 1. That's f of 0 and f of 0 plus h. And remember, it's greater than 0, so we're using the sine function, not the negative. Okay, then this just becomes the sine of h minus 1, and then a negative, that's 0, and a negative times a negative is a positive 1, so that's just what comes from here. Well, what do the 1's do? The 1's cancel or become 0. Negative 1 plus 1 is 0. So I just end up with the sine of h over h. And what's that limit as h approaches 0, even from the positive direction? It's 1. So notice again what we've got. We've got a left-hand limit of negative 1, a right-hand limit of 1. All right? So since both one-sided limits exist and are unequal, negative 1 does not equal 1, we have a corner at x equals 0. So we can say that p of x is differentiable for all x except for x equals 0. Okay. Sounds a little more interesting. I hope that makes sense.